How's it going, ladies and gentlemen? Mr. Johnny here again, talking to you about ideal gases. So we're going to look at real and ideal gases and kinetic molecular theory. So objectives of this video, hopefully you guys are able to describe how a gas behaves and describe what a perfect or ideal gas would behave, what it would look like. All right, so ideal gases. So a perfect gas, how would it behave? Well, the first thing is it would definitely travel in straight lines until it hits something. So it wouldn't be like a curveball. It's going to go straight until it hits, say, another gas particle or a wall. It's going to go in straight line until it hits something. It is also going to have molecules that are so small that it takes up no volume, right? They're going to say, hey, they're going to shrink and they don't take up any space, right? Bloop, nothing there. So the gas particles have no volume in a perfect gas. They also lose no energy when it collides with something. So if we had gas particle collide with another gas particle, it's going to transfer that energy so that none of it is lost, right? It can transfer the energy to another one, but it's not going to lose the energy. They also have no attraction for other gas particles, right? So they're not being pulled together at all. There's nothing there. There's no attraction. There's no attractive forces. That's in an ideal gas. They also move faster as the average kinetic energy increases. Remember, average kinetic energy is also temperature. So basically, the hotter they get, the faster they move. So why don't we take a look at a simulator. fet.colorado.edu has a lot of really good simulators. I urge you to check them out. Let's check it out. So here we got a container, and here we got an air pump or a gas pump. So I'm going to pump in some gas, and I want you to watch what the particles do, how they behave when they first come out. Straight line until it hit the wall, right? They keep going straight line until it hits something. So let me add some more in there. Right? They all go into a straight line until they hit something, and you can see that no energy is lost. Now you may start to see, hey, but Mr. Donahue, some of those particles are going slower than other ones. I thought you said they didn't lose energy. They don't, right? That one right there that's like not really moving didn't lose energy. It was transferred to another gas molecule. So another gas molecule is going faster. If you were to take their average energies, it's still the same, right? You can also see they're also kind of different too in that these are real gases. And you notice like, hey, I can actually see those particles. The particles actually take up space. They have a definite volume. What you don't see here though, that's true for real gases, is there is also some attraction between them. So in real gases, there is attractive forces. Remember the London dispersion forces, even between nonpolar molecules, they have attraction. All right. And also watch what happens when I introduce another type of gas in there. All right, are they going to stay separated? Are they going to be homogeneous or heterogeneous mixture? Well, they're going to become, just by themselves, a homogeneous mixture. They're going to mix evenly, so it doesn't matter where you take a sample from, everything's evenly distributed. All right, so let's go back, talk about, all right, well, real gases. So we were talking about perfect conditions for ideal gases. A perfect gas would behave like this, but we don't live in a perfect world, right? Real gases don't behave like perfect gases all the time. So how are they different? Well, first off, they have particles that actually take up space. They actually have a volume. Those things are there. They take up space. So we can't ignore that. They also have some attraction to other gas particles. Remember, like I said before, even if it's just two nonpolar gas particles, there's going to be London dispersion attraction between them. So there is some attraction. So the question becomes is when are gases the most ideal? When do real gases behave like perfect gases? Or first, when you have low pressure, which makes sense when you think about it, because what do gases want to do? They want to spread out and get far away from each other. So if you got low pressure, there's nothing forcing them together, so they can spread out more and be more like a gas. Secondly, high temperature. Why? Because, well, let's think about this. How do gas particles move? Fast, right? So if you increase the temperature, they're moving even faster. So I draw more lines to show it going faster, right? So that would make it behave more like an ideal gas. And the last thing, last condition, is when they're small, right? So the smaller the gas, the more ideal it is. Because remember, Smaller gas particles have weaker attraction, weaker London dispersion forces between them than bigger molecules that have more electrons and are more polarizable. So you get stronger attraction between them. So the smaller it is, the higher the temperature, the lower the pressure, the more ideal that gas is going to behave. And then one last thing about gases, we got Avogadro's hypothesis, which says equal volumes of all gases at the same temperature and pressure have the same number of molecules. So if you were to double the number of molecules, you would double the volume. Basically, it's saying if I have 1 mole of H2 at a certain temperature and pressure and volume, well, it's going to take up the same volume and have the same number of particles as helium under the same conditions. So it doesn't matter what gas I put in the balloon. If I put in 1 mole of it at the same conditions, they're going to take up the same amount of volume, right? So you can see they're the same size, taking up the same space because they're all 1 mole. Now, if we were to say take 1 mole and put it in a balloon and take 2 moles and put it in another balloon, well, the size of the second balloon is going to be twice as big. Use twice as much gas, it's going to be twice as big. All right, so I hope you found that helpful, and I will see you in class. Bring questions. You stay classy.